Now let's have a look at this problem. There are n items numbered from 1 to n with item I having a weight of wi and a value of vi. Taro has decided to choose some of the n items and carry them home in a knapsack. The capacity is w and the sum of the weights has to be at most w. Now it asks, find the maximum possible sum of the values that Taro takes home. And let's have a look. So there's not a lot of memory at all. I'm pretty sure the intended solution was to not have it as an entire 2D array, but it turns out that we can exploit it, and we can exploit this, or just forget about it, and it'll actually run in time. So we said that we wanted a 2D array with the size with. All right, let me just write this down here. 2D array. One dimension has number of items currently considered, and then that goes up to n. And then the other dimension is all the possible sum of weights that we are looking for. So that'd be up to capital W. So then, let's have a look. So first thing we do obviously is fast input, because that is very necessary, especially as the problems have huge amounts of input. If it's above 10,000 or greater, I seriously recommend that you use fast input. Otherwise you might run into issues where you don't know why your time limit is exceeded, but in reality it just fixes fast input. Quick question, am I cutting out at all?
No.
Okay.
Not yet.
Good.
That is
You're
great.
good to go.
That is great to know. All right. So we said we have ints capital N, capital W, and let's go back, and then item I has a weight of wi and a value of vi. So I'm going to store it as a int wi and vi. Those are the things I'm going to generally need. And as I mentioned earlier, I would recommend that you declare, like earlier as in a few weeks ago, I would recommend you declare your really big arrays outside of the int main. So ints are knapsack, and typically replit will pass replit will be fine if I had n and w declared up here. If I had int n, not ubt, int n comma w up here, and I put n and w as my things, it would run. But in compilers such as things such as MSVC, which is another thing, like if you use VS Code, you're going to run into a problem where these numbers are not necessarily constant, so they're not going to it's not going to allow you to do that. So the size, I'm just going to do it as 101 and 1 and what was it, 10 to the power 5, 10 to the power 5, so 5 zeros. And an important thing to keep in mind is you should keep it slightly bigger than 110 to the 5, like make it like 105 or 101, and then so add 5 to your array sizes, just so you don't have like an index out of bounds thing should you forget that sometimes it could be indexed from 1 to n, or if it's indexed from 0 to n minus 1. To not run into that problem, I recommend just having plus 5 or plus 10 on each of the dimensions of your arrays. However, but that's not going to give a huge impact on your memory unless it's very, very, very tight on memory. So we're going to first take in our inputs. Take in n and w, not that, cn, n, and w. And we said before that, so let's just fill our array. So there's this thing called memset, where it takes the thing that you're trying to set, so our container that we're trying to set, so in this case it's knapsack, the value that you want to set it to, 0, and then the size. And so you could do 105 times 10 to the power of 5 plus 5. But there's a shortcut to it, which is, if you want to do the entire thing, size of knapsack. However, keep in mind the mem set, when you take this, I'm not sure, wait, which, like, if you do 0, it will actually assign them all to 0, but if you choose, like, out of the numbers, like, if you choose, like, 2, and you want to set everything to 2, then it'll be really goofy, and I'm not sure which base it was. Can someone remind me, like, what base does it set it in?
It says every character. Yeah, it says every byte.
Untitled Chapter.
Oh, it says, yeah, it says every byte to that. So
Yeah.
it'll be really goofy, so I recommend you use this only if you want to do 0. But if you don't want to use memset, that's perfectly fine, because we can just run a quick for loop. Int I equals 0, I is less than 105, and I wish I could type I++ for int j equals 0, j is less than 10 to the power of 5 plus 5, and j++. And then it would similarly be knapsack, not that, knapsack I and j equals 0. So you have two options. You either use this memset, which I'm just going to clear out so people don't get really confused, or you use just a regular for loop. But if you're going to use anything except 0, I just recommend using the for loop. It doesn't take that much time to code or to write out. Okay, so now we've set all of our values to 0, and the idea of knapsack is numlock turned off. That's not good. Okay, idea of knapsack. We either, for every current item considered, you either choose that item. So knapsack at I and j equals, and then you go 1 up, knapsack I minus 1, j minus current weight. Wait, and that's because you want to go up, and then left your current weight so that you can add that on, and then you have to add the value of your current item, value of item, or if either not optimal, if that is not optimal or not possible due to not being high enough in the sum of weights, then you want to do knapsack at I and j equals knapsack at I minus 1 and j, because we're saying that our maximum value for the first I items being considered with the total sum of j, the maximum value is going to be the same as our last one, which was with the first I minus 1 items being considered, therefore not considering the current item, with the same sum of j. And so we want to take our input now for everything. So you could store all the weights and values in an array of some sort, and manipulate that way. But I find it that you don't necessarily need to, because you can just take input and just do all your weights and values right away. And I just realized there are some people who have actually solved both these problems. I did not consider them. And so if you've already done those problems, before I keep going, I would like you to ignore everything I'm saying until I call you back, and try DMLPC C13C3P5. So for those brave people who've already done DP, both knapsack 1 and knapsack 2, I want you to try that problem while I'm taking up these problems, so that you're not sitting there and being bored. Okay, so now we have to take input. So for int I equals 0, I is less than, here's the thing. That brings me up to an idea. When we take input, or like when we take our first item, if we did 0 index base, like we used to go from 0, 1, 2, 3, dot, dot, dot to n minus 1, then you would have to do knapsack at 0 and anything would need a separate algorithm. Not necessarily that bad, it's really just filling the first sum, like knapsack I, and then the weight of first item would be filled all the way till knapsack at I to weight to total sum of weights. So that is the possible idea for if we want to do zero indexing for the I one. But instead of doing that, if we just started at I equals 1, 2, 3, dot, 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 to n, then the algorithm is going to be the exact same for all. What is that? Why does that keep happening? Then the algorithm will be the same algorithm for every I value. Does anyone have any questions so far? So this is how we're setting up our knapsack, and so I'm going to choose, so I'm assuming no one has any questions. So since it's the same idea for every I value and not an edge case of, knapsack at 0 and then this thing is different, because I can't do 0. The reason I have to do a separate algorithm is because if I want to do 0 minus 1, that's out of bounds. You can't have a negative index, obviously. So instead of doing getting to that mess, I'm going to just index my index from 1, 2, 3, dot, dot, dot to n. So now I'm going to take input for I equals 1, I is less than or equal to n, and I plus plus. And the reason I go less than or equal to n is because I want to include n, because I'm not doing 0 to n minus 1, I'm doing 1 to n this time. Now, so now we can take our input, and they were called weight I and value I. So Cn, Wi, and Vi. So now we have successfully finished our, we've got our input. Now we have to actually implement this idea of the knapsack over here. Quick test, am I still clear perfectly? Like, can anyone not hear?
Yes.
Okay.
We can hear you.
Fine.
So now that we have our input, we want to do our second dimension thing. We have to check for every total possible sum of weights. So we have for int j equals 0, and you have to start from 0 because there might be an edge case in a problem where something has a total weight of 0, and you'd obviously want if let's say that specific problem wanted you to maximize the number of items you could take while being under that total sum of weights, then you would obviously want to include that. So we just start from 0. J is less than or equal to W and J plus plus. So now we are going from sum of weights 0 to max sum of weights in this dimension. Now, there was two cases that we know before. Knapsack I of j equals knapsack I minus 1 of j, or knapsack I of j equals knapsack I minus 1 j minus current weight plus the value of the current item. So we're going to quickly implement that. So instead of doing like a max, like you could simply do max I and then I minus 1 j, like the index is I minus 1 j. This is just a rough sketch. Comma I minus 1 j minus weight of I plus weight of item plus value. But this j minus weight of item over here, if j was equal to 0 and your current item was had a weight of 1, then you'd be an index out of bounds 2. So we don't want to run into that. So instead, we're going to have an if statement. If j minus weight of, no, not weight of items. I was literally writing what it said. If j minus wi is greater than or equal to 0, then we can do our assign it to the maximum out of the two possibilities. Knapsack I of j equals the maximum of knapsack I minus 1 j. That's the one directly above us for not including. And then for including, it's knapsack of I minus 1 j minus, and then the weight of the item is wi. And then we have to add on our vi because that's the value of our current item because we're adding it to our knapsack at that point. So knapsack I of j would become maximum of I minus 1 of j, or I minus 1 j minus the weight of the current item plus the value of the current item. And otherwise, there's just only one thing it can be assigned to, which is knapsack I minus 1 and j, because you can't include that item. So you just use the one from above. And so at the end, we would have to just simply print out the maximum value that we have determined. And that is simply done by cout knapsack of n and w. Notice how I'm not using n minus 1, w minus 1 because I have been one indexing the dimension for n, and the other one is from 0 to w. That's not one indexing, but the thing is, I was considering all possible sums, so 0 was a possible sum, so I have to go to w, and then our new line character. Most problems typically don't require you to put a new line character, but there are some where the judge literally says you cannot submit it without our new line character. So that is our knapsack 1. Anyone have any questions? Fear not, I'll paste the code right now, just so people who couldn't finish copying everything can have a look at it whenever they want. But,
not copy word for word. Just please not copy and paste.
Yes, don't copy and paste. Bringing up that topic, when you're submitting DMOS problems, I advise you to try to solve it on your own, and then get a hint if you are really stuck, you've tried for a really long time, but don't copy anyone's solution, because then you're simply just not learning at all. So take a look at it, and also try not to copy it word for word, otherwise they might be like, are you cheating or something? Are you copying off someone? They don't know that we're in a class, obviously. They can't guarantee that. So that is going to be our code for knapsack 1. Now for knapsack 2, I guess I'll just open a new file. Actually, let's just test it and make sure it works perfectly fine. I don't want to just give you bad code. So Replit doesn't allow you to control V for some reason, but one of my great friends, which I won't mention his name for purposes of privacy or whatever, unless he wants to blurt out that, hey, it was me, he can do that if he wants to. You have to actually right click and go to paste here. And so that's 90. And let's just do this wacky one over here, because that seems like a really weird one that you may not understand. Now we try and see if this will work. And yay, you get 17. So that's our thing. So I believe that this is good. But actually, let's have a quick talk about our solution. So this will pass, but if there was a memory constraint that was much tighter than this solution, we would have to do like a memory constraint that allows us that memory constraint such that of NW memory doesn't pass. Because obviously it'd run a memory limit or exceeded. So if we had that problem, and obviously this being a 2D array, it does take up a lot of memory. You could calculate the exact amount on your own, but I'm not going to do that. If you had a problem with the memory, then you have to realize something. Knapsack of I, in general, the array knapsack of I, is only related to knapsack of I minus 1. And that's because we see that in our for loop. So then, in order to simplify, like in order to bring down our memory a lot, we realize that if we had an I equals 5, let's say, then we said that knapsack of 5 is related to knapsack of 4. And then after, in our next version of the for loop, say the value for n is like 100, knapsack of 6 is related to knapsack of 5. So we're simply taking our old, like the one that we built, we simply build it, and then we use that for the next one. And then that next one is being used for its next one. So if you had two arrays, K1 and K2, and then you did something like K1 of I and J equals max of K1 of I minus 1 J, and then alright, this is not K1, this would be K2 because we're saying K1 is related to K2. And then the other possibility is K2 I minus 1 and J minus Wi weight plus val. If we did that in our for loop, and after we copy K1's values, into K2 and then reset K1's values to 0, then we essentially shift K1 over to K2, and that's K1's getting reset, so it'd just be filled with zeros. And as a result, we can do our next thing. We can do our next thing in the for loop without actually using any more memory than just these two arrays. So the size of the arrays would obviously just be K1 with size max, like sum of weight, so it'd be 10 to the power 5, and then K2 would be the same size. So we just knock out our for loop that like we did up there, but then we assign K1's values to K2, and then we make K1 all zeros. And then, but with that, by using that, we're only using 2W total memory in arrays, which as a complexity would be O of W, because O of 2W is just O of W because we don't care about this coefficient of 2 on the W. As one of my teachers said last year, going half the way is going like all the way. So if you had O of half W, it's the same as O of W as well. But I hope that you guys have finished that. I hope you guys have understood time and space complexity by now, and big O notation in general. But this is the idea of how to to greatly bring down your memory usage, because before we were using 100 times the sum of W. Now we are using 2 times W. So that's clearly a lot less memory. So yeah, I would recommend thinking about different approaches to cut down your memory, and this is just one of them. But for different problems, if you ever have like a memory limit exceeded, try to see, if I can use my thing only relate to certain other things, that I can copy the values over and then reassign our original array, or the one that's being changed. So that is knapsack 1. Anyone have any questions up until like this point?
Sat, can you check test case number 2 code?
Test case number 2. What?
Can you just submit the code?
Why, is something wrong with it?
I don't know, my replit might just be messed up. Yeah, that's what I
You are
got.
right.
Long loss.
Yes.
I think it's because, yeah, longs.
Okay. So he makes a good point. You see how these numbers are really big? As a result of me being careless, these things should be longs. Long knapsack 105 to and 10 to the 5 plus 5. because we're actually overflowing from our integers. And when you overflow from an integer, like let's say your maximum was like 5, if you counted 1, 2, 3, 4, and then you reach 5, it would actually go to instead of exceeding the maximum value that an integer could take, which would be 5 in this case, but this is not actually what an integer takes in C++, it would go to -4. It would go all the way to the minimum value in the negatives, and then therefore it wasn't taking anything after 2 billion to 20 billion, something like that. So yeah, make sure you use longs. It still won't use that much memory, but it will still pass under memory limit. But obviously, this is a much better memory use thing, and because of that, I'll try. Did that work, Arslan?
I'm pretty sure this question you need to do the memory limit thing, because I might just.
Long longs don't work. Long longs don't pass under the memory
when
limit.
I first tried it, like a long time ago, my memory limit always exceeded unless you use the.
Wait, try submitting the code.
I'm pretty sure.
It's pretty weird because Kevin.
I got it with long.
You got it with long?
Yeah.
And a 2D
I had to
array?
do.
Yeah. Oh wait, 2D array? Oh,
Did you use the efficient method or did you use the regular method?
I just did it.
I had to use the efficient method.
Alright, let me just log in real quick. Let me see. So yeah.
Oh, I didn't use it. I used. Oh yeah, it's 1D. Oh, never mind.
Oh yeah. So yeah, it won't pass under this solution. So yeah, this solution will not pass. As an exercise, try to optimize memory usage. So yeah, I'm not going to go through and change everything right now, but I feel that I gave a good explanation, and that just so I don't give you all the code, you guys should go ahead and try doing using 2 arrays like I did instead of a 2D array. Thank you, Arsenal, for pointing that out, and so that this thing is actually important, because now there's a real case as to why, as to where it won't work. Anyone else have any questions or any concerns?
How'd you make your demoj input thing look cooler?
Huh?
It's black. Mine's not black. Like it starts.
You can change.
Okay. Let's go through this right now. All right, so you go to my thing, edit profile, and we go to the editor theme over here, and I chose Tomorrow Night Blue.
Oh my god, I didn't know that was a thing.
Yes, if any of you have not caught on, coders like everything dark. Not to be racist. But yeah, that is our Knapsack 1. Now, I assume you guys want me to go ahead and do Knapsack 2. Because obviously you guys wanted me to take up Knapsack 1. I might not go through it, but rather give you the idea instead. So give me 1 second. Views, orders. And then, okay. So, I know some people who've had trouble with Knapsack 2 even after they finished Knapsack 1, because and that's understandable, since I introduced the idea that you use N and W as your array bounds. But let's have a look at this. We have N is from 1 to 100. W is a huge value of 10 to the power 9. And then we have that is the same. But our values have went from 10 to the... I'm pretty sure they went down from 10 to the 9 to 10 to the 3. Yeah. So yeah, the values have greatly decreased from 10 to the 9 to 10 to the power 3. So we have to use that in some sort of way. And we can, and right away looking at it, we have W's at worst case 10 to the power of 9. And if you convert that to convert that to gigabytes or megabytes, it would use 1 gigabyte. But DMarsh has its optimizations. But the memory limit here is 256 megabytes. So we clearly cannot even try. We shouldn't even try using O of W memory or O of NW memory, because that would like definitely not pass. So instead, we have to use the fact that these values have gone down and n has stayed the same. And the worst case scenario, if we had n and v, is 10 to the power of 5. Which I think would pass even as a 2D thing, but we can use a 1D, we can use a 1D memory optimization if we wanted to. So I'm guessing that you guys want me to take this up as well, or give you at least the idea. So I'll go ahead and do that. Add file. nap2.cpp. Okay. Give me 1 second. Yeah, I think we'll do this in 1D because just in case I don't want to do the same thing again, and also give you an idea of how the 1D actually works. So our template stays the same using namespace std int main. Gordon, can you make a poll for me? Go to.
Yeah, sure.
Okay, I just want to know how many people have finished grade 12 computer science or are in grade 12 computer science right now.
Wait, do you want it so that it's only 3? You want 3 options where it's you're in, you're currently.
Just the way we've been
done
doing
it.
is fine.
Okay, so like, are you currently?
And guys, go ahead and answer that
taking-
poll while I get the template set up. I'm just curious as to that, because I do want to teach concepts that you might have learned, that at least people who have already finished ICS4U would already be familiar with, sort of, but I want to introduce it anyways. I just want to make sure I'm not boring making people bored. Senior polls. Okay, so there's quite a bit of you in both ends of the spectrum. And, Arslan, did you send me anything important, or was it just the problem that we had before?
I wouldn't look at it on stream.
Alright, bet. Making sure that the OBS is still on. Okay, we're good. Alright. Yeah, I probably shouldn't.
Cut that. Cut that.
Yeah, never happened. Okay, so same idea. Let's get our input N and W. CNN and W, and int WI and VI. Okay.
Sorry. Technology can be replaced.
Pardon? Did someone say something?
I clicked on Junior voice by accident, but it's nothing to worry about.
Yeah. If it's just a quick accident, you don't have to mention it next time. It's okay.
Yeah.
I trust that you know what you're doing. Alright, so, this time we have to take a slightly different approach, obviously because OW memory simply will not pass. And you might have had trouble thinking about it while you're attempting to solve the problem, if you did solve the problem. But obviously this time we are going to need our long array, and 1 second. Okay. O of W memory will not pass. Now we have to use O of. We want to ideally make it O of V memory or O of NV memory. O of V memory or O of NV memory, where V equals sum of the different VI values. So this time, instead of trying to do everything all at once, like how I was able to just take in the input and taking the input and apply it right away, I'm actually going to store all the weights and values. So knapsack 2. So I'll actually store it as a pair of so what came first, the weight or the value? The weight came first. So I'll store it as a pair of long because that one, the weights are the really huge ones, and then int and INP for input, sure. And then size of 101, or yeah, let's just do 101. Okay. So let's first take in our input, and then this would become irrelevant. So by doing this, we're just taking our input and storing it so that we can use it nicely after. So for int I equals 0, actually let's just use one indexing again because it worked out nicely. Your algorithm doesn't change much if you do one indexing, but I feel like for knapsack problems it's generally easier to use one indexing, but that's just my personal opinion. Because you're taking the first item, not the you're taking the first item, the first two items, not the 0th, and then the 0th and the first. Like that just makes less sense, even as someone that uses 0 indexing most of the time. So we're gonna take in our input of I, not O, I and first, and then input of I of second. Remember that we're using a pair, so that means we have to access it with dot first and dot second. So yeah, and also I don't have to make variables like int v, take the input, and then assign input I dot first equals v or something like that. I can just take input like this directly. So I get all my input now. So now we have all that taken care of. So clearly, oh shoot. Can you guys still hear me, or is it just Replit that's just...
yeah, we can hear you, don't worry.
Okay.
I hear you.
Alright, so let's just hope that Replit doesn't die. Okay, we're back online on Replit. Now we have to actually think about a different way to store this. So if we try using O of V memory or O of NV memory, we need a different approach. Anyone that has solved this problem, do you want to give a hint or explain the idea behind the O of V or O of NV approach? Now the real question is, did anyone actually solve the problem?
Wait, which question?
The knapsack 2.
Oh.
Oh, okay. Well, Eston did it.
I'm working on it right now.
Okay. No matter.
Yeah,
it's
Eston
okay.
has.
Okay. No one has to.
Eston has the best time, so Eston has one of the best times, so
Yes, it took me on. So, you have like a roll, right? You want to go from the very last to very first. So you put the first one at 0, just basically query from forward to backward and see the highest, the lowest amount of weight it takes for like the very last one, and then go back and back. That's what I did.
Mm-hmm.
I think that makes sense. And then the spare one. So like I just did it the reverse way of like what the first one is.
Yeah, I see. That's not a bad approach.
Yeah.
Okay, so yeah, you have the idea of I've seen that you have the idea of store the best approach of store the least weight that you can get on every index. Is that what you're saying?
Yeah.
Okay.
Like every index means like every value, right?
Yeah. Every index.
Yeah.
And the indexes, indices are every possible sum of values. So if you're able to do this, and then let's say we implement such a program, and then we work it out, and then blah blah blah, our final answer would be back to front, or going from maximum sum of values to going from the index of maximum sum of values backward, and finding the first index such that there is a sum of values that is less than W. Because if you fill your entire table, you do all your operation, whatever, you want to maximize the sum of values, obviously. So you want to maximize the index that you're looking from. So you start from your maximum sum of values, or just the sum of all your values, and then you work back, like you keep checking backward to see, at this location, did I encounter a sum of weights that's less than or less than or equal to our W value? So that's a general idea, and estimate is completely correct. So let's actually store our sum of values. Int sum of vals. And our in our pair we stored our, I should probably comment this, pair of weight of item, and then this one was our value. So that's what we're doing. So obviously we want to work with the second. So into sum of vals, let's just set that to 0, and then for every value that we input, let's increment to our total sum of values. Plus or equals input I dot second. So yeah, that's the general idea of what we want to do. So we want to find a way, so we've successfully thought of the idea that we want to do. We want to use the values and then determine at which points can we minimize our values for the index. So let's go ahead and get that started. Now obviously we need our array. So we have 10 to the power 9 as our total sum of weights. So I'm guessing that we're going to need long, knapsack or array. So let's just use array this time, and with the size of our maximum value of the sum of weights. So for every item, there's 10 to the 3, and then there's 100. So you actually have 10 to the power 5. Because you multiply each of them out, because if you have 110 to the power 3 sums, then you can get at most 10 to the 5. And that would be O of NV memory approach. Now, as we see, we clearly don't have an O of V memory approach, but we will be perfectly fine with just an O of NV approach. At least I hope. So we've made our array where this is the sum of values, our indices, and the thing it holds. I don't want to say value because that's values mixing up. The thing it holds is maximum sum of weights. Okay. Now, for every item that we get, so for int I equals 0, or for int item equals 0, item is less than n, item plus plus. And I just realized that we actually one indexed everything, and like I said before, it's not necessarily really. So since we one index everything, we have to use that same approach with one indexing. So we have item equals 1, item less than or equal to n, item plus plus. And now let's have a look and see what we can do. So we have our, so what would happen is, let's just put a comment in there. For every spot, for every spot, you want to check back and see if the current weight is less than the previous, less than the sum of see if the current weight at the index, or which is the sum of values, is less than the sum of the weights of the previous index or previous sum of values plus the weight of current item. And now we need to make sure that we're critical on our array, because when there's strange behavior. So some compilers set their array values default to 0, but some compilers set them to completely random values. So actually, before I go ahead and do this, I actually want to make my entire array filled with I++. We want to make that array filled with really huge numbers this time, because we're trying to minimize the sum of weights. So we can just do direct comparisons by saying, let's just make this as really big as we possibly can, and then for every single item that we add on, it'll be easier to compare rather than saying, hey, let me just set it to 0 or -1, and then not, if I haven't visited there yet, I temporarily set it over. So you don't want any of that mess. And but in this for loop, I have done for int I = 0. Now we know that if you don't take any items at all, you actually have if you don't take any items at all, you have a sum of weights of 0, and you also have a sum of values = 0. So that means that array at 0 should be 0 as well. Now effectively, I could have just done int I = 1, I is less than 10 to the power 5 plus 5, I++, but I you know what, that's probably a better idea. We should do that. For int I = 1, I is less than 10 to the power 5 plus 5, I++, we set our array to be L long maxes so that we can do comparisons and take the minimum one every single time. And I should mention that in C++, there are these max values, and for the long, it's L long _ max. And you can search up the different names, like for the integers, it's int _ max, all capitals. And then for long, it's L long _ max. For longs, it's long _ max, I believe, but I have previously mentioned don't use longs because they're very unreliable. So we have our array 0 = 0, and now we can finally get started.
It's only unreliable on demoj. The demoj judge will either do long as...
Yeah, depending on the problem itself, it will either be 4-bit or 8-bit, or no, 8-bit or 16-bit. Am I mixing up? No, 4-bit or 8-bit. So it will either be the same size of the int or the same size of the long, and you don't want to take that risk. So just use long every time if you want to use longs. So don't use longs. That's the summary here. So for every item, you want to get the cost and the value. For int item = 1, I is less than or equal than I++. Now we're working with each of the items with a certain weight and a value attached to it. Now we say array at I. No. So the idea that we want to do is we want something like array at I equals the minimum of the current value in the array, like the thing that the thing at the index it's holding is a sum of weights. So you actually want to minimize the sum of weights for every index that you can. Minimum of array at I, comma array at I minus value plus weight, where the value is the current item's value, and W is the current item's weight. And let's think about if we did something like this. If we said for int I = 0, I is less than some weights, or let's just do 10 to the power 5 plus 5. Actually, just do 10. No, actually, no. Why am I thinking so hard on this? For int I = 0, I is less than our sum of values is sum of vowels. So I'm just going to copy that. I is less than sum of vowels, I++. And you actually want to include the sum of vowels because it's valid to have total value with the sum of vowels. Obviously, you can include it if you want to. If we did something like this and then said array at I equals array at the minimum of, I should probably knock this on the side and knock this on the side so I have room to write. Minimum of array at I, comma, array at I minus, and then our thing is called INP. INP of I dot second, because the first was the weight and the second was the value, so we're working with the current item. So the current item's weight is INP I dot first, and this one right here is the second. And we're working with the indices in I minus INP of I dot second. So you want to do I minus INP dot second as the index plus INP of I dot first. If we did something like this, there is something wrong here. Does anyone know what's wrong? If I went from 0 to sum of vowels. And that is perfectly fine because you don't come across this dilemma or situation often. So let's say we had our...
Hold on, I might know.
Wait.
What is it, Evan?
Yeah.
Can you? Is it like you can use the same item twice?
Yeah, that's actually true, because let's say you had something with an item that had a value of 5. And so if you're at index 5, you could say array at 5 equals the blah 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 blah, and then it would potentially get assigned to array at 0 plus weight of item. But then that's for I equals 5 in this for loop. But if we got to I equals 10, we'd say array of 10 equals blah 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 blah, and it would potentially be array at 5 plus weight of item. The thing that's wrong with this is that we update the array at 5 before we even access it again. And we can't do that because we're trying to do the same. We're trying to change everything with one item at the same time. Meaning, like, let's say array at 5 had an old value and now it gets reassigned. It had an old value of x, a value of x, and now it got reassigned to y. Now when we got to I equals 10, normally we want to work with the same x value in here because we don't want to change multiple things at once. We're trying to change one thing and we'll add the item only once. But in fact what it's doing is it's not taking x, it's taking y, because I equals 5 in our for loop will come before I equals 10. So you're essentially applying the effect of the item twice onto this, whereas the item is only used once. So that's our problem. Now our solution instead is to reverse it. And the reason why that works is because if we did I equals 10 and then I equals 5, we update array at 10 according to old value of array at 5. And then the plus the weight of item, but that's not really necessary. But then here we update we're updating array at 5 to a new value according to array at 0. But we're updating I equals 10 first because that's coming first in our for loop. And with that effect, what we're doing is we're actually making sure that our old values are being changed first, and then we're changing those values from the previous in the knapsack that are previously held in the knapsack. So, as a result, instead of going from I equals, you should be increasing, you should actually be decreasing. And that actually has many applications, such as I know people who have finished ICS4U have had this problem. I forget what it's called exactly, where you delete something from a list in an increasing for loop, like you delete an object from a list. If you don't understand what I'm talking about and you haven't finished ICS for you, you don't have to understand it really. You delete some object from a list. If I could spell, in an increasing for loop, and then when you got to the next one, you had some error. Anyone want to remind me what that was called? If anyone remembers. That's fine. I'll post it in the note. But you had an error, or when you got to the next one, or got to the end.
Index out of range.
Yeah, index out of bounds or something like that, because your range keeps changing, and then you like.
Yeah, it's short.
Yeah, index out of bounds.
Yeah, and then it gets completely messed up. So a solution to that, like we're going to do here, is to go from the back or the highest value all the way down to the front. Since when you delete something from some sort of list, only the indexes of the values above it, or like with indexes higher, are going to get affected. The stuff before it aren't going to get impacted. So that's got many applications. So in this case, we want to just do int I equals sum of vals. I is greater than or equal to 0, and I minus. So in this, what we're doing here instead is we're going from the highest value to the lowest value, so we don't prevent any of this thing from happening where you use an item more than once accidentally. Now, there is one problem here, which is I just talked about overflow when Arslan had a concern of it not getting to 5 billion or something like that in this compilation right here. If we're going to have an overflow up here, when we assign Ri to L-long max, the value of a long can't get any greater. So, unless you use an unsigned long, but the reason why, so it can't get any greater. So when you add something to the highest value, it'll go all the way to negatives, and it'll completely screw everything up. So what you can do here is you either set this to a slightly lower value, or you make the long array of 10,000 or 100,000, 10,000, 100,005. Instead, you make it an unsigned long. And if you don't remember, an unsigned means there's no positive or negative sign. It's essentially positive, so you have one more bit to use on something else. But we're just not going to worry about that, and we're just going to make these array values some really high number. So let's count the number. So we said our sum of weights is 10 to the 9, or yeah, my bad. Sum of weights is 10 to the 9, so let's make it like 10 to the power of like 13 or something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we set array of I to some really large value that it won't overflow and go into negatives, but it also will never be reached and won't screw anything up. So we have this simple line. We set it to either that, or you go back to the value and add on the current weight. So that's the general idea of it. Now that we finished that, we finished that part of the for loop. That'll actually execute everything we want here. Well, we'll get the least weight of the values on every index, because we're looping through each of the items and we're applying the change where we set it to be the minimum of what was before it and adding on the current weight, or just keeping the current value. So that will actually sum everything up for our array. Now our goal is to somehow get an answer, and we've already stated somewhere over or I don't remember, I can't find it, I'm just blind probably, but we've already stated that we have to find the maximum index, or the highest index, that has a valid sum of weights, aka less than or equal to W, because that will be our final answer. That results in the index that we found it at to be our final answer. Okay, and then so that's pretty straightforward approach. You want to go from the highest index possible. So for int idx equals, or just go int I. For int I equals, and the thing was called sum of vowels. Sum of vowels I is greater than or equal to 0. I minus minus. Did I seriously type it wrong? Yes, I did. I didn't camel case properly. And then we just want to check if the if array at I is less than or equal to our total sum, and we know our total sum of weights that was permitted. Then print that print the index, because that's the desired thing that we're looking for. And then we want to just break out of the for loop. So we could either just do break, or we can just say our return 0 here, because this would just leave the int main function, because we give a return value for int main, and stop any processes that are happening. But I'll just use break. And then our final line, which is optional, but for good convention, I'm going to put it, our return 0. Anyone have any questions on what I've done here? Because I know it's been a lot.
Can you use memset to fill the array with like the high number?
Yeah. Remember that it adds it onto every bit. So I think if you do it as 1, it'll get it to a high number that'll be great. Like memset it to 1. I think it'll get to a number higher than 10 to the power of 9, but I'm not sure.
Okay.
But yeah, we just use a for loop is the safest method, but I think it will work.
It definitely will, but yeah, use for loop.
Okay, yeah, but I'm not sure of the value on top of my head, but that's why I just use the for loop. But yeah, you can use the memset if you want. I typically use memset only if it's 0, and that's really just to make the code slightly shorter. But if you're wondering about very that's such a very small difference in length of code, it'll be kind of useless. All right, so we have this as our code. Now let me just try submitting this, making sure it works. I really hope it works, otherwise I would have completely screwed up something. Of course it doesn't work. Now let's try our test cases. Did I mess up anything that I can find right off the bat? Alright, let me paste this code. And can anyone see something wrong immediately? Let's post on senior. Messages over 2,000 characters. Great. So that it's going to be pasted as a file. Let me just check the test cases real quick. Paste. By the way, while I'm doing this, can people have I had any moments where the mic cut out a little bit or what?
I think you're good. I didn't cut out at all.
That's good to hear. And what's not good to hear is the fact that my thing is literally not working.
Your mic hasn't cut out yet.
Alright, well, I don't know what's happening, to be perfectly honest. Let's have a quick look at this. So we set it over int I equals sum of vowels, I is greater than equal to 0, I minus minus. Oh, over here. Alright, so this is the case that I didn't handle this case, where if I did I minus input of I dot second, it would actually give an index out of bounds because you'd be going to the negatives. So instead, I'll just do I is greater than or equal to input of I dot second, because then I minus input of I dot second, if you subtracted that from both sides of the inequality, you get it as greater than or equal to 0, and it would work. I really hope that's the only issue here. But who knows? Let's give it a shot. Okay, that's not good.
Unfortunate. I'll look through it.
Okay, I think for now we can leave it. I'll find the error and then post it after. But does anyone have any questions as to like the idea of my solution? Okay, looks like there's no questions. So, wait, let's have a look at what this says. Okay, until then, Gordon, can you put up a poll? How many people are more comfortable than Knapsack now than they were before I took up the questions? You hear that, Gordon? Hello? Am I still here, or is he?
I don't think he's in the call.
Where did he go? That's great. Okay. Okay. I'll just do it myself. I'm sorry I don't know how to use poll, so. Are you more familiar, or are you more clear on Knapsack than before I took it up? And then second question, do you guys have permissions to react?
No, we don't.
Are you serious? Okay.
If you react to it, we can add on to it.
Okay, don't.
We can add the reactions and then we can react with them.
Alright, let's do. You know what? It's okay. I think. Alright, is anyone still confused? Because I can go over it again, but if you guys don't ask me now, I won't know your situation. Okay, I hope that means you guys are good with it. But now, we should get onto our last part of the knapsack, actually. Okay, where am I looking at? Let's go to Word. Okay, so, honestly, I didn't think I was going to get to coin change and hashing. If people who know hashing, you might be curious as to why I'm teaching it so early, but that won't be something we will cover over until next week or something. Okay, so as said, I hope that you've gotten clear at least, or finished the problems, DPD, and like the 2 knapsack problems, and get to it soon, after class, or just make sure that you have it clear by next class. Because if you don't, then you're gonna fall behind a lot. All right, so let's think of a scenario in our knapsack. Let's actually go to our Replit. And then let's say we use our same input as our Alright, so we have 38, 330, 450, and 560. And I'm just going to add some names over here. Josh, Kevin, and who wants to be mentioned? Anyone want their name?
Me.
Alright. But you already have your name on here.
Oh.
Kevin. That's you.
Can you just put it twice?
Me.
Who said me?
Me. Evan.
Okay.
Wait, is my name in there?
No, you're good. Alright, I'll just use these 3 names now. And now, if I asked you, these are the different names associated with the items. Print out the maximum value of the item, and then list the names of the people, wish I could type, of the people that, list the names of the items that we put. List the names of the, of the items, that's sure. I don't want to objectify you, I'm not saying you guys are items, but I can't really think of a way to say it. So list the names of the items. So now we have to think slightly differently. So we have to go back to our idea of what the knapsack was. So for every possible pair, I, comma, j, so for every thing, every index I, j in the knapsack array, you had two options. Either include or don't include the item and make your knapsack or your k I of j equal to k of I minus 1 of j, where j is the same sum of values and I is the number of items considered, hence the I minus 1, suggesting that we are using everything except the current item. Okay, I typed everything twice. Alright, so that was our first option in our knapsack. And our second option was, let's include the item and make k I j equal to k of I minus 1, because we're going back to our previous amount of items, and then j minus weight of item plus our value of item. So if we had to find the names of the people that have done this, like that have participated or have contributed to the filling of the knapsack at its most optimal thing of maximizing value, then let's start with two variables, x and y, and x equals n and y equals w. Our total number and then our sum of a total number of items and our sum of weights. So to backtrack, so we're gonna so the idea is fill out the table like we did in knapsack 1. Like just fill it out like we normally did. Don't worry about the names. And then you want to store, but at the same time, obviously store the names in an array so that you can access them later on with the same indexes, like without mixing it up. Like you want to keep it the same name pointing to the same item kind of thing. Okay, so now we have our x equals n and y equals w. So the idea is if for every x and y, if k at x and y was equal to k of x minus 1 and y, that means that they didn't use item, and therefore this person should not be on the list of this name should not be used or included because we didn't use them. But if they were not equal, kxy is not equal to kx minus 1y, then that means that we used the item with the associated name and we should include them on the list. So you include them on the list, and then your x and y have to go to different locations because now you had to go back and see where, if you didn't before you included them, where were you before. So include them on the list and make x equals x minus 1, because now we're going back up one item, and y equal to, and then the way we did it as j, like we did k of I, j equals k of I minus 1, j minus weight of value, j minus the weight of the item plus the value. So that means that we have to make y equal to what it was before. So it would be whatever this j value was. So it'd be whatever y currently is minus the weight of the current item. So essentially what we're doing when we do this is we're going back to where we would have been before, including like before we chose to include the item of where we're at now. So now we're literally just going in reverse. So we made x equals x minus 1 and y equals y minus the current weight of the item. And then I forgot to put it here. Now you have to make x equals x minus 1 now, because now you have to check again with the same sum, the same sum of weights. Therefore y equals y. So y won't change in this case, in this first case. So you keep doing this. Keep doing everything I said in the curly brackets until you get to when x equals 0, because that means that when you go all the way back up to x equals 0, that means that we weren't considering any items up there. So that means that we weren't doing anything. So once x becomes 0, then we can successfully write down all, we successfully located, or we've written down all the names of the people that we have put down, like the names of the things that contributed to the maximum sum, because at every point you want to have the maximum sum, and so it's either it's the same as it was before and they didn't contribute, or it's not the same as it was before and you have to go up and left because they contributed. So it's the reverse step of what we've done before. Now so then you would so then after you just print out the maximum sum that we get in the table and the list of names, and it might be in order or it might not be in order. So this is the idea of what how to take to backtrack and say, did I include this person or did I not include this person? Anyone have any questions up to here?
Can you show this with like an actual example?
Like, if I were to actually write it out?
I mean, like with the Josh, Kevin, Evan, and like how you would backtrack to find the names.
That's a good idea.
Yeah.
All right. Let's go to Word, and don't worry about this note. We're probably gonna get to that next week. So let's insert a table. It's actually a really good idea. Thank you for suggesting it. 9 by 4. Okay. Let's make this a bit bigger. And let's get our simple input down here. Okay, that's not what I wanted. Okay. Sorry for the terrible formatting. So if we were to we have to fill out our array first, so I'll just go ahead and do that real quick, or at least I'll fill out this one. If no one has any questions, or if everyone understands how the knapsack works, I'll just go ahead and fill out the array real quick for the preliminary step. All right, I'll assume no one has questions, so I'll just go ahead and fill it out. This will be 0, 0, and 0. So and this will be 0, 0. This will be 30, 30, 30, 30, 30, 30. And this will be 0, 0, 30, 40, 40, 40, 70, 70. 0, 0, 30, 40, 50, 50, what? Oh wait, no, that's not 40. That's not 50, it's 60. I'm sorry about that. And then so 70, and this is 90. Alright, so I hope that you guys understand what this is. So, like, obviously this is our sum of weights, and this is the number of items considered.
Chat?
Yes?
Sorry, where did you get the 40?
You know what? I wish I could read. I thought that said 40 because I was putting together this 4 and this 0. So you're definitely correct.
Oh, okay, cool.
Thank you for telling me. No, if ever I make a mistake, please tell me. Because otherwise it'll just get chaotic, I'll mess up, and then that won't be good. Alright. So we have our input here. I don't think anything's wrong, but please, once again, please tell me if something is wrong. Okay, so let's go ahead and this is going to be 80. Okay, so as Rayton suggested, we should probably go ahead and simulate this. Now I won't write the code for it because that's going to be an exercise for you. However, I am actually, as of right now, I'm setting up, like I'm putting up all the problems on our new judge, or like it's not new, but to like not the demosh, it's the dom judge. Insert row above. So I will have I'll have some practice problems on everything in general. As soon as I can. I'm guessing it's gonna be Friday. So, and then I'll make it so that you can do it for like the next 1 or 2 weeks. And then let's insert a row to the left, or a column to the left. And then Control V, 0, 1. Okay, what I hit? Okay, 1, 2, 3, and then let's center that. Okay, so in this case, so I hope everyone's clear on what this is. So in this case, our x equals, oh man, this the auto capitalization, please just handle with it because it's just going to keep coming and coming. So x equals 3 and y equals 8 because we're starting at the very bottom over here. So now we go ahead and check is, and I'm going to call the array k, is k at, I should probably use a coding font. Console, okay. Is the array k at 3, 8, is that equal to k at 3 minus, we check upward first to see if we didn't use the item. 3 minus 1, 8. So we check above and see if they're equal, because if the above one is equal to the current one, that means we didn't use the item. So is it equal to, is 90 equal to 80? Definitely no. No. So therefore, we have to reassign x and y. So x is obviously going to be reassigned to just the row above it. So x equals 3 minus 1 equals 2. And y, x equals 3 minus 1, which is equal to 2. And y equals, now you have to go from here, and then the weight of this item was 5. The weight of Evan was 5. So that means you have to go up 1. Like, so your y has to go back 5. So you're over here now. So y equals 8 minus weight of Evan equals 8 minus 5 equals 3. So now y gets reassigned to 3, and now we're going to be over here. Let me just highlight the spots that or underline the spots that we're at. So now x and y is going to get reassigned to that. And at the same time, add Evan to list of names. I hope that's clear. Anyone not understand?
Wait, does this mean that if we want to backtrack, we need the memory the NW memory?
Unfortunately, yes.
Okay.
I'll never give you a problem where you need O of W memory and you need to backtrack. I don't think there's a way to do both unless you use some really weird method, but I will never ask you that. So now we're at K of 2, and our index over here is 3. So K of 2, 3, and now we have to check if it's equal to K of 2 minus 1, and the same spot is 3. So you have to check if that's true. So we check if 2, 3 is equal to K of 1, 3. And clearly they're equal this time. That means in our knapsack thing, we did not even, we could not add the person because he was either unoptimal or not possible. So that means, so yes. So therefore, X is going to get reassigned to a row above it, or the value above it. So 2 minus 1 equals 1. And Y equals 3 stayed the same. So then that means that Kevin did nothing and would get, I won't say won't get carried in the project because the knapsack is carrying technically, so he didn't get carried. Had to make the pun there. So now K2, 3 is equal to K2 minus 1, 3. Yes, that means that X gets reassigned just to a row above it, and Y will stay the same. So that means we're going to just relocate from here just up to here because we did not include the item. So Kevin did nothing. So the only.
But what was the pun?
Pardon?
What was the pun that you made?
I said that Kevin would have gotten carried, but the thing is, knapsack, you're supposed to carry the knapsack, so you can't necessarily carry Kevin. So.
Okay. I don't get it, but okay.
Double-edged sword. Yeah, don't worry about it. So we're going to reassign our X and Y is that X equals 1 and Y equals 3. Now that I'm thinking about this, X and Y should have probably been switched because this is like the vertical and this is the horizontal, but I hope that you guys still understand, and just to not confuse everyone, I won't do anything. Now we have to go to K of 1, 3. Did that switch font? Yeah, okay. K of 1, 3. And you check if it's equal to the one above it. So you're checking if this one right here is equal to this right here. K of 1 minus 1 and 3. And obviously, on a good day, 30 is not equal to 0. So that means no. And as a result, we can say that X is just going to move up 1. So X equals 1 minus 1 equals 0. And Y equals, and now we have to go left the current weight, the weight of the item that we're at, and the weight here is 3, and so the weight is 3. So you have 3 minus 3 equals 0. Yeah, 3. Let's just, I'll just write 3 minus 3. 3 is weight of Josh, and then that equals 0. So we'd add, what's his name? Josh to the list of names. And now we're at X equals 0. Whoops. We're at X equals 0 and Y equals 0. And now that means that we weren't even considering items up here. We only started considering items when X equaled 1. So that means that we're done when X equals 0. So in this case, the printout would be 90 and 90 and the names of the people were Evan and Josh. Let's just put them with a space. Evan and Josh. Now sometimes like I might assign the question that's gonna be in sorted order, and just keep in mind in like you can sort strings. You don't have to like do a comparison thing. You can sort strings either using a vector, like the same method how you sort a vector of integers. You can sort strings in lexicographical or alphabetical order. So so your output would be 90, Evan, and Josh, and then the order of the names is tentative, obviously.